Right. So I wanted to talk more about stable envelopes, since they appeared many times in the discussion, and I want to give another partial discussion of this. So let's take a simplest example. Well, I mean something just to look at. So let's take C star P2, and on my P2 I'll have an action. I'll take just a one-dimensional torus, maybe something like this: A inverse, A minus 2. So this is in GL3. And then there is another torus that scales in Plekti form, but will be not needed in what we're discussing at this moment. So if I look at the equivariant K-theory of X, well, this is generated. This is generated by. So this is generated by. So maybe I'll write generated by one element X, which maybe I'll call O1, and satisfies the relation that product of 1 minus X times AI inverse. I in this case goes from 0 to 2 equals 0. So if we look, so this is defined, this is a union, so this sits the spectrum of that spec of this guy. This sits in the product of my torus, so this sits in a product of my torus T, actual torus, and one more variable. I'll just write maybe C star. This where this X sits. And in there, it's a finite. I mean, it's a collection of copies of T. So maybe I'll draw a picture. So if I have, maybe I'll write. So maybe if this is axis is log A. There's maybe other coordinates, but I don't ignorant of them right now. Over 2 pi I, and this is log x over 2 pi I. Then this means that in these coordinates, these equations are linear. So you have x. This is a union of three copies. X can be a, 1 can be a, k be a squared. So in logarithmic coordinates, this is going to go. This corresponds to fixed. So in general, the spectrum of this is always the union. This is always equal to the union of the spectra of components corresponding to the fixed locus, and these are the three fixed points of F. And here the 3 fixed points are, well, there's the x equals 0, so x equals 1, there's x equals a, and then there's a equals x squared, so this looks like this. And so we see that in this union of different components corresponding to fixed loci, there's some intersection happening, and the intersection happens exactly where I pick up extra components. Like here I get this, I have this point, I have this special point which corresponds, the fiber of the scheme over any point A. So if I have some point A, then the fiber of that scheme over that is just the K-theory of the fixed locus. And when this fixed locus jump, some of these branches come together. Like if A is A is a order 2, so this is the point where A squared equals 1. And so if A squared equals 1, then I get one more 1 here, and I get an extra jump in fixed locus. And if A is 1, well, that's like the whole thing is fixed locus. That clear? So in other words, this spectrum of covariant K-theory is some scheme over my torus, and it has interesting behavior precisely over the hyperplane arrangement that we discussed before. And so what is
Now, is it true in any some sense that everything is determined by coordination one?
I don't know. I mean, there are theorems to this effect, but I'm not sure what the most general hypotheses are. Like, for example, if I'm in this Goreski-Kotvitz-McPherson situation, when not only the fixed points are isolated, but also the fixed curves are isolated, then it's clear, yeah. And so what's a stable envelope? A stable envelope is, in this language, stable envelope, it has data, that cone, so this is a cone. This is one of these cones that sits in the Lie algebra of A. It's one of these cones there. And it has a slope, which I think in Roma's notation slope was maybe lambda. Maybe I'll write it. Slope sits in some alcove in pk(x) times r. This is a specific map from K theory of the fixed locus. Maybe say one component of this fixed locus, so it's just you can pick any one component. To the K theory, this whole space. And so what this means that this is you given a function on one of these components, you should be able to continue to a function on the whole scheme, such that it vanishes. So this has support. This is determined by support normalization and degree condition. So this is the, what do they say? They say that this is, so you have a, so let me highlight one of these components, maybe the middle one. So let's say this is my component f. I have some function on this component, and I'd like it to extend to the function on the whole scheme. And the condition is that first I have to have a certain support. Second, the normalization says that the extension, well, there's an extension whereby just if I restrict it back to the same component, I'm picking up the equation, the weight of the normal in the normal locus, in the normal bundle, too. So in other words, this near that same component is given by the correspondence with just attracting manifold, and therefore. Meaning, if I take this function restricted back, I mean, sorry, I don't mean it's an extension. It says you have a map such that if I take a function here, I restrict it back to the component where I started, then I'm getting getting multiplication by the normal, by the Euler class of the normal bundle, which is specific polynomial on this scheme. And then the crucial condition, the degree condition, is that I've restricted to some different component. That as a polynomial in this variable a, I satisfy a certain bound. So in other words, if I look at the degree of this stable envelope of some component f, and I restrict it to some other component f prime, say I started from this, and this is my f prime is my horizontal one. Then this is the degree in A. In general, means a degree of around. This is a function of torus. So its degree. This is really a Newton. This is really a Newton polygon. And this Newton polygon is supposed to sit, where is supposed to sit? It's supposed to sit inside just you start at this component here. You have its own normal weight. You have its own. So this sits inside the degree, the A degree of just maybe I'll say attracting manifold of f prime, restrict back to f prime. So this is a polynomial function of degree half the codimension of this fixed component plus a certain shift. This is already this was just discussed in the Roma's lecture. And I'd like to.
So shift was dependent on I.
Yeah, right. So the shift was this piece of data, the cone that went into the support, and the slope that went into this shift.
This depends on the shift is not apparent in the cohomology level.
No. Yeah. And so now what I'd like to say, rather than trying to say more about this, I'd like to advocate for a more general construction, and which is also easier to explain. And that is, if I take that scheme as is, and reduce all coordinates mod q to the z. So if I take spec of my K-theory and reduce mod q to the z, and I can do it because it sits in the product of tori, all defined by monomial equation. I can do that. So this will be now sitting.
What is Q?
Q is what?
What does it mean to reduce mod q to the z?
What about what?
I mean, it projects to. I mean, all coordinates project.
Oh,
to,
I see what you just
yeah.
take the
You
function.
yeah, that's what it means. I mean, it's also. So Q is just. So I just take some random number. Less than 1. Right? So then this will be sitting. Well, this will be sitting in a product of elliptic curves, which is abstractly is like the co-character lattice of my torus O times E. So this is the current variables live here. Times. So in general, so this is what does it mean? What does it mean that? What do we know about K-theory of Nakajima variety? They're all generated by tautological bundles. Means the generalization of this picture, instead of O of 1, I have to take the Chern roots of all tautological bundles. So I have a Chern root of a bundle means symmetric functions on symmetric polynomials on a product of C star. So in general, I'm getting a product of now symmetric copies. So the ranks of the tautological bundles are VI. So SVI of my elliptic curve E, where E is just C star not Q. So the exact same picture will be now. So you can read the exact same picture, thinking this is a part of an elliptic curve, except of course now there'll be, instead of 2 special points, we'll have 4 special points, all 2 division points. So in general, so this is we had this hyperplane arrangement. This induces a natural arrangement of abelian subvarieties in the product of elliptic curve. Yeah. And now, I'd like to argue that this condition, this kind of degree condition, is yeah.
What would be I then?
So X is in general a Nakajima variety. It has tautological bundles of ranks Vi. So it means the Chern roots, before I reduce mod Q, the Chern roots of the tautological bundle there live in the symmetric product of C star. When I reduce mod Q, you get the symmetric product of elliptic curve. And so what I'd like to argue is that this condition here, it's much easier to phrase it so now one can ask for a similar map. So then it will be now you'd like to map. You can't really map you can't map global sections, but you can map sheets, right? So you'd like a section of a home map between some sheets. So they may not have global sections, but the home sheaf will have sections. And so now let me explain how to think of this condition. Why is that easier in the elliptic situation? And so maybe I'll first. So yeah. So if I have I'll start with the following, maybe again like a Whittaker-Watson style statement, which I'll then explain in more modern language. But you can ask, so specifically, if I think of my elliptic curve as C star mod Q, then I can think of sections of line bundles here as functions here that are automorphic with respect to shifting the variable by Q. So I haven't said anything profound. And the basic, like elliptic functions, or maybe Mumford's lectures, like on page 1, or maybe in Whittaker-Watson on page 1, you can see that if I look for where's my basic thing which I wanted to quote to you.
Page 1.
Yeah, right. Well, maybe it's in different. Could it be in a different textbook? Interesting. Hold on, I'll try. Since it's an elementary analytic statement, it's not some equivalence of objects. I better have it. I better write it correctly. Yeah, here. So if I look at sections, I look at section-specific line bundle. Namely, I'd look at sections, functions, solutions. I look for solutions of f qz equals. So I want a degree n bundle. So this will be z minus n. This is degree of the bundle comes in, and then there's some automorphic constant lambda, which is times f of z. Or you should think of lambda as sitting in the universal cover. So lambda sits in C star, which again projects by the same map mod Q to pick 0 of your curve. Okay. And solutions of this as Q goes to 0, which is in the end we would like to recover our original C star in the limit when the elliptic curve degenerates to a nodal curve. So we'll send. No, we want to 0. In this language, it's better to 0. Yeah. So that's because you see, you'd like to this would be this Q. This is a parameter that rotates some loop that maps to x, right? Yeah. If you want to go to x as a fixed locus of this action, you don't turn the equivalent parameter off. You send it to infinity. And so then, so this goes to the span of monomial, so the span of z to the k, where k belongs to an interval alpha, somehow belongs to an interval from alpha to alpha plus n. And what is alpha? alpha is the limit of the real part of lambda, log lambda over the later part of log q. Right? So what you should take away from that, so remember when we take, this kind of window condition says that you have a polynomial with exponents sitting in a certain segment, or a polytope in general. And that this you can view if you think of if your C star as a limit of elliptic curve as q goes to 0, you can view being a condition of just being a section of a certain line bundle. And this condition is analytic. It's only in this condition is somehow smoothly analytically interpolated between all chambers, whereas in the limit you have to pick. It starts jumping. So the way to think.
Should one of the brackets be for square bracket?
Right. Well, let's say it's generic, then it's correct. Yeah. But in general, they both. I mean, they. Yeah. So you have to think a little bit.
Probably.
Yeah. Let's say it's generic. This is somehow. And so the way to think about it. So we have. So of course, we usually think of like elliptic curve. So this is q equals 0 curve, and there's a nearby q equal non-zero curve. But if we think of this as a quotient by q, maybe the more accurate picture is you take this. So over complex numbers, this is a p1 with 2 points identified. It's a sphere with 2 points identified. It's always p1 with 2 points identified. And then, so what sits, if you in this presentation, what sits in the middle is an infinite chain of p1s. And the generic fiber is C star. So this is my C star, which is a cylinder, on which I have translation by q. And then q degenerates. I have a chain of p1s where they have a z action, just takes to the next one. And to say in which interval my lambda bundle is gonna fall is a question of into which one of these components. So this is C star this C star parameterizes line bundles. So I have my lambda sitting somewhere there, and to say where is that, into which one of this is going to go. This is the kind of thing that happens. In other words, in elliptic situation, so as elliptic curve degenerates like this, you get from analytic families, you get discontinuous objects, and you get objects that jump. Is that clear? So if now we go back to this example. And what we would like is a map of what we would like to have. And then we have the elliptic guy. So now I'm going to try to edit this board. And so first exactly, yeah. So I'll start here. The degree condition is the condition of the kind I wrote down here, so that the monomials fall into a certain window. And the replacement of that is just this is a section of a suitable line bundle. Parameterized by a point now. So this will be, so now, okay, I'll take this. This will be a point. Now I'll call. So maybe I can still call it slope. I can call it slope, but now slope sits in. So this will take care of itself, but this slope slope sits by slope. This will sit in pick x 1 times elliptic curve. So this stuff here will be apart. So this will not this scheme. Who knows what its actual peak is? It's in some singular variety. Who knows what's the peak? But it will sit in peak 0 of the elliptic cohomology of x. So it will be a map from here to here. So previously this slope parameter corresponded to a line bundle, and the way we used that line bundle was that to use the weights of that line bundle at different fixed points to designate the shifts. But now we're going to use we have a line bundle. We make it elliptic by taking a variable here, and what we would like is to produce a line bundle on the elliptic on the scheme, and then designate this to be the step. I have to modify the stuff here, but this would be a section of a certain.
So there are no longer separate fixed points at all. You don't have to do it fixed point by fixed point.
It's still a map from. You still go from sections of some line bundle on a fixed component to section of some line bundle on the ambient space. Is that the
condition was for each fixed point in the boundary?
Oh yeah, for some restriction. Yeah, so that's universal, exactly. That's a universal statement. And how is that and this is
LTX, so what it is?
What?
What it is LTX?
It's just so this is it. So you take this. I mean, in general it has a definition, but for Nakajima variety it's just reduction of this mod cube. Yeah. What? No. Now the elliptic homology is by definition a scheme. There'll be a scheme, so it's easier. Otherwise, yeah. So elliptic homology is a functor from spaces to, in general, super schemes, and that functor is covariant. So you take functions, you're going to get a contravariant function, but in this case there'll be no functions. And the way, so how would that map look? Well, it's very easy. So you see on this, if I have a line, so if I have a, say if I have a vector bundle here, and this is in Victor's, this is the wonderful source of the wonderful, still Victor's paper with Capran and Vassarov, still wonderful read on this subject. So I very much recommend that. So you know where we're going to get line bundles, on this guy. Well, you know, we're just going to get it from here. So this is the vector bundle, has some churn root, and then has the determinant, which means that this guy maps just by the summation. This is the sum of churn roots. And then if you have an element of peak 0 of your elliptic curve, which is an element of elliptic curve itself, you can just pull back it there. So this assignment is easily seen to be just linear over peak. So it really defines a well-defined map from peak x tends the elliptic curve into this piece here. So this is a line bundle of degree 0, and then we have to what we have to do is we have to like this normalization. What's it going to be? What will be the statement of normalization? Normalization. So what does it mean, normalization? Previously in Euclidean K-theory, how did normalization read? It says if I take the stable envelope, so maybe we don't need this part. Maybe I'll erase this part. So again, still in K-theory, if I take the stable envelope of some class supported at F, so I'll just write stable envelope of F, and restrict it back to F, or maybe I'll write alpha, and some class alpha. So then I get this alpha, this is an element in K-theory of the fixed locus. And I restrict it back to F, I'm going to get alpha tensor product over all repelling weights. So I'll write their weights in the repelling normal bundle. So take the normal bundle, the repelling part, the normal bundle to the fixed locus inside of F, and I have to put 1 minus W inverse. The analog of this formal in elliptic homology is that I'll just have to take the theta function of W. And then you see that, well, the theta function is a section of a non-trivial, the theta function is a section of a degree 1 bundle on an elliptic curve. And so this is, while we're discussing peak 0 here, there'll also have to be bundles of positive degree for this map to work. And what are the right bundles? The right bundles is, see here we get, well, what's the degree of the bundle here? The degree of the bundle has to do with, you take 1/2. So the repelling part is 1/2 of all normal weights. So if you choose a polarization, which is polarization, this is, we'll write half of the tangent bundle of X. This is a global choice of a half of the tangent bundle. So this is an element. This is an element in K-theory such that this guy plus its dual, maybe I'll write H bar inverse times the dual, is equal to the tangent bundle of X. This is called polarization. Then, so Nakajima varieties and other things we discussed, they always have it, because if you have it, or if you have a cotangent bundle to something, then, well, a cotangent bundle by definition, you can choose either the fiber or the base as a half of the tangent bundle to the cotangent bundle. And if you have a Hamiltonian reduction, you get a similar choice. You always can choose half of the tangent bundle. And so the right object is to map. So if you map, so instead of saying take half of the weights that are different between, so you have a normal bundle is the tangent bundle to the fixed component minus the tangent bundle, rather tangent bundle to the whole thing minus the tangent bundle to the fixed component. Rather than say, well, I'm going to choose a half of the difference, let me just take the difference of the halves. So this would be saying, so this is for every, right. So there are two general things. So if I have a vector bundle, so in general, if I have a vector bundle, let's maybe call that vector bundle. So these are the churn roots of some vector bundle. Maybe I call that vector bundle V. So this map to the elliptic curve is the elliptic analog of the first Chern class. And there's a different map, which is an elliptic analog of the top of the Euler class, which says that the section. So I can define theta of v to be a bundle whose sections. So if these are xi's. So maybe I'll write it like this. So if I have. So if xi's are Chern roots of this bundle here, I hope you can see it, then the first Chern class is a line bundle whose sections are theta function of the sum of the xi's. Sorry, no, this is not exactly correct. Sorry, this is not right. But because this here I want to pull back the degree zero bundle. But the theta class of V, and I think this is called Tom's class in Victor's paper. This is a line bundle whose sections are product of all Chern roots of. So this is a bundle of degree, which has to do with in the first approximation the rank of this object. But degree of a bundle on a labile variety, it's generally it's an element in some group, which you can write down in terms of what it is. And so the right map here is the map that I'm going to go from half to half. So I'm going from theta of half of polarization of the fixed locus. And if I have a polarization of the ambient space, I automatically, if I have a polarization of the ambient space, I restrict to a fixed locus. I take the fixed part of that. This will be polarization of the fixed locus. So this has polarization, and so then this goes to the polarization of the function of the whole space.
What is theta? It's a sheet.
So theta is as defined as a line bundle. So it's a line bundle on the spectrum of elliptic homology, which is defined for any element in K theory of X defines you a line bundle. And so but then it has to move. So there's some line bundle. Maybe we'll call it LS. So it's some element here. So this is some positive degree bundles, and we tensor this with this LS. And then this has to be. It's a good thing to do it. Is also tensor this with this LS here, but then with some shifts, which have to be. It's very easy to see that you don't put the right shifts. So you have an abelian variety, and you have another torus that maps it to pick 0. You can shift this universal bundle by appropriate element of the base, and you need to put it here for this to work. But maybe we'll not. These shifts are the origin of the fact that this is. So if all of you are familiar with elliptic quantum groups are always dynamical. There's always, when you write equations, you always have to, like you write a Young-Baxter equation, you always have to put some shifts in the variables for them to work out. And this is the need to have a section like this. You need to put a shift. You need to put a shift here in otherwise it's not going to work, and these shifts will propagate into these dynamical shifts in order form this right. So this now depends. So this now still depends on a cone, but now on this variable it depends analytically. Analytical on this. On what it used to be, the Okounkov thing, this is analytic. Exactly, yeah. This discontinuity will come in the asymptotics, yeah. So this is it's a very familiar case again in sort of classical analysis that you get a discontinuity from like, you know, think of gamma function. Gamma function is an entire function. Well, if you look at the Stirling formula, it has a square root. So
Do you have any kind of differential equation in this parameter?
in Q,
Yeah.
not that I know of. All right. So now, what is this? What is it one would like to do with this, and what is that? What is it good for? So, the main application of the main application of this. So this can be used, since this gives you, if you write R matrices, this will give you this kind of dynamical R matrices. You can use this geometric way to do representation theory, much like envisioned in this paper of Victor. But I want to bring it back to enumerative situation and explain the role of this object in enumerative situation. So I have 15 minutes remaining, or when did I say? What? 20, okay. And so, remember, yesterday we had some discussion about what's the enumerative meaning of various difference equations. Or rather, up here, maybe. Guess I shouldn't have erased this, but anyway, I did. So, we discussed what is the meaning of equation, but maybe let's just now talk the meaning of solutions. So, we were discussing this kind of cohomological field theory, and various particular computations of cohomological field theory give its operators gave us operators for some Q difference equations, but you can also similarly construct solutions to this Q difference equation. What you do is you can consider geometry where I have one blue point and one white point. I didn't explain how exactly moduli spaces are compactified. I mean, what are exact moduli points? But maybe it's too late in this sequence of lectures. They play a different role. And now, so by construction, the singularities of the quasi-map were never allowed to go get to a blue point, but they could get into a white point. But now inside my moduli space, inside quasi-maps from this, so you have quasi-maps from this to my x, or of course to define quasi-maps you need to embed x in some stack, but we had this discussion yesterday. So in this moduli space, like I said, you can have a singularity hitting this point. But inside of this, I can consider a locus where I prohibit exactly. Maybe I'll write Q map, quasi-map NS at this point wide. Is that precisely the locus where this is precisely the locus where the red points are prohibited from going into my white point. So this is somehow the map means it's regular. Here, no singularity here. This is an open set. And
points.
Yeah.
You bring it to go.
Exactly, yeah.
That's all.
So in the basic observation that goes back to the very, very classical work of Giventhal is that, while this is an open set, if you consider situation equivariantly with respect to rotation of my P1, this open set will have proper fixed loci. Just because what can happen at the fixed locus? The fixed locus is that these guys are prohibited, so they have to somehow chase the blue point. And as the blue points will bubble off, and so this will be all proper. And so this defines, so it means in localized, if I work in localized case theory, then the evaluation push forward of my symmetrized virtual sheaf times z to the degree. This will be a well-defined operator. So this is, since at the 2 points, I'll write it as an operator. So this is an endomorphism, belongs to the endomorphisms of K theory of X. That will bracket Z. But this part is localized. Maybe times C star Q equivalent. Okay. So in other words, this will be a series of the exact same shape as like the series of some hypergeometric form. So this is summation over n, so to speak, z to the n, and then times rational function of equivariant variables. So this is rational. So in this is a rational function. This solves. This is the fundamental solution. This is this. For those of you who attended the lecture, the colloquial lecture, this is the fundamental Z solution of the quantum difference equations, and that is holomorphic in Z in some neighborhood of origin. It has some rational functions, coefficients in equivariant variables. And the point about this whole point about the main point about elliptic stable envelopes is that if I apply this operator to, so this I can apply, this adds an equivariant K theory, but I can, so there's a, it also I can apply to there's a map from, so if I have elliptic, so elliptic functions, I can view as functions on C star. My main construction is that my scheme is a reduction of the spec of this object mod Q. So any function there, I can just pull back to a function here. It will not be a polynomial function, but it's still a function. And I can still act. So if I apply to stop elliptic stop with this parameter z of some class alpha, maybe I'll write some class gamma, where this is a class supported on the fixed locus. So in this elliptic envelope, I get a variable, which is exactly the kind of variable I want. I want a variable which lives on the universal cover of my Picard, which is my original. So this Z sits in peak X O times C star, and this projects taking mod Q goes to peak of my. This is exactly the choices I want. So I can apply this operator to this elliptic stable envelope, and the basic somehow geometric thing is that this will have no poles for some properties reason. And this is the maybe it's too late in the talk to discuss it, but there's some in the end. In the end, this is constrained by. Well, anyway, there's some. You'd like to show that this expression. So this, if you hit it with this, this has this application. This has no poles. There's no poles for a going to infinity and some maybe going to 0 in the direction specified by. So this has a cone, and the direction specified maybe to be precisely maybe minus cone. I don't remember the exact notation, but not so particularly important. If I send the covariant variables to 0 in some specific way, to go to infinity in some specific way, that means that the kind of since the support condition of my elliptic stable envelope will prevent from the end point of a curve to go in some directions. And then you can see that this will be, in fact, I mean, you can show that some work. You can show that this is a proper space. So in general, there's a great virtue in geometric representation theory because it predicts that some, I mean, used this way, it predicts that some, if you think of this as enumerative interpretation, it predicts that some computations are nice. So it predicts that some computations, for example, do not depend on certain variables. So they, say rigid, for example. I mean, incidentally, rigidity works beautiful in the elliptic situation. We'll get, maybe we're not going to get that. Yeah. So then, and then it's the job of the geometer to actually invent the corresponding setup, where you know something's going to happen. You know something's going to be we'll have no pole, or will not depend on a certain variable. In this sense, you'd like to have this object have no pole. Well, the way to prove it, you have to show that once you go into the nuts and bolts, there's in fact there's a proper interval.
And so what is the representation theory's meaning of having no pole?
Oh, because this is going to be, this is the half, so like I explained yesterday, once you show this, you know it's a half of the monodromy. And you know the monodromy of like QKZ has to be elliptic R matrix. So this is the guiding principle that you'd like to, yeah.
Is this no pole thing related to this relative compactification of the evaluation?
No, this kind of no poles it has to be exactly as about. There's no compactification. These things can go off to infinity, but can only go off to infinity in some ways that are anyway. We can discuss it later. And so that means that this object, this means that this is the fundamental A solution of the same equations. And this tells you two things. This tells you that, like I explained, the monodromy, this means that the monodromy of this equation is given by a product of two such things. So this gives you the Gauss decomposition of, so the monodromy gives Gauss decomposition. And since on the other hand, the product of the ratio of two stable envelopes is the elliptic R matrix, that tells you the monodromy of this equation in A is given by the elliptic R matrices. That's one thing. It also has a nice three-dimensional interpretation, because what does this mean? You have this counting problem, which in this open situation may be saying like you count disks. Somehow you take your position on a disk with particular boundary, position function on a disk with particular boundary conditions. And so this is maybe called disk position function. That says that this means the equations, like we discussed, the somehow common thread of this lecture is that these difference equations should be under this Zeiberg Relegator symplectic type duality, that guess the Zyberg interrogator is the first paper where this is, or that, or anyway. Anton is maybe a Zyberg interrogator, Kapustin, somebody. Anyway, there's this. We have a. So there's this duality. That means that this object here will have to go that this is the same partition function in dual geometry. Because has to be so the equations are the same, but the solutions are different because one is a holomorphic in Z, the other holomorphic in A. And that tells you that this guy is really the, and so then you think, well, what is this guy supposed to do? This guy is like so okay, I have 5 minutes left. Plenty of time to say things that are impossible to explain in any finite amount of time. Is that this is why elliptic homology? Why do you get elliptic functions? Well, because this three-dimensional theory, they should have a category of boundary conditions. So which complicated categories, maybe Anton will say something more about them. But in particular, they have to assign something. So remember, we were thinking of this is my Riemann surface, and then the whole three manifold. So maybe we had like three manifold was this Riemann surface cross S1. So when I talk about boundary conditions imposed near this point at infinity. So for this three-dimensional theory. So when I talk about boundary conditions imposed near infinity, so if there's some circle I want to cut out, then means, so this if I cut out a little circle, the boundary of this manifold is really, well, it's obviously S1 cross S1, right? So the boundary of S1 cross S1. So I'd like to see some theory that sits on just on a torus, right? So this is a couple, and a candidate for what this category is our coherent sheaf of a certain kind on this Kapranov-Vissarov style loop space. And you see that somehow makes sense because you have evaluation map. You have a real evaluation map not just to X. You have a evaluation map onto this loop space because you have a quasi-map. Even here, you have a quasi-map with some potential of well, maybe here. So if I have a quasi-map with potential of some poles wandering in, this really goes to like a formal neighborhood of polynomial loops inside all loops, which is what that space is. And in fact you're gonna where you're really going to go universal cover of that, because this is where the variable z, this was variable will be remembered by that variable z. And so really you're talking about sheaves. So the right objects to consider are sheaves on this kind of loop space that in particular have prescribed their graded with respect to many things, including a grading by lattice peak x. And if I act by deck transformation, I'm supposed to the automorphy factors that I was picking for this elliptic stable envelope, they should really be coming from just corresponding shifts of the grading in the sheaf. No, I mean not yet. No, not after that. And so then, this is really saying that this is a way to write boundary condition in one theory in terms of some other boundary condition in the other theory. This says that and the elliptic stable envelope is really a functor from boundary conditions in smaller theory to boundary conditions, a way to extend boundary conditions in smaller theory to bigger theory. And I'll maybe conclude with one remark that there is a very simple statement that that will prove. So I mean, as it stands right now, I mean, I wish I could say we have a uniform proof of this duality between difference equations for all cases, which maybe like Adavesh says, if we somehow if we were all locked up in a room and not, it was like a quest. So we were locked up us in a room, and then we there's with no exit until. Yeah, but what should really, but the real, if you don't want anything categorical, if you just want a numerical statement of symplectic duality, then all you need to produce is really the mirror. So what is it? What you need to produce is the mirror interface. What is that object? It's an elliptic class on X cross X check. So this is the fixed points of here. The fixed points are here in bijection. So maybe I'll write P and P prime. These are fixed points of the torus, such that if I reduce this mirror interface, I reduce, I don't know, interface I. We reduce I to one thing, then I get the stable envelope of the other thing. So that's right. So this is and in Voronkin down for hypertoric varieties, one can write down just explicitly. And I'm sure it exists in general. I don't have an abstract abstraction to that. Because then what would be the logic? If you have this, guys, then this tells you the monodromy of the two equations are the same. From the knowledge of poles, you conclude the equations are the same, and then it's all downhill from there. Of course, maybe you'd like I said, there's some possible categorical lift of that, which I'll lift other. Maybe I'll be happy with just numerical statement right now. So
numerical statement would be some computation X is the same.
Yes, no, this will imply for all. This will imply for all. For all, this will imply the isomorphism. So you have some cohomological theory for X, and you have a different one for X check, and this will imply so I should say this is a purely classical statement. There's no curve counting in there. This is just about the interaction between elliptic homology of these two spaces. And if one can write it down, then which I'm sure it exists. So really from the physical point of view, it's a way to match the boundary condition of two mirror symmetries. But I'd like it in numerical. So it's a numerical statement in a sense that it's a statement about, in some sense, classical cohomology of these two spaces, or maybe some elliptic lifts of this classical cohomology, and that will imply the curve counts for all. This will imply the isomorphisms of the two theories that I explained, because everything is reduced to these very basic blocks, and this will show the equality of that basic block. Okay. Maybe that's the way to stop here.